In this video, we'll be solving trig equations with identities. So first off, let's talk about what an identity is. An identity is an equation that is true for any value that the variable is assigned. So for example, if we had the equation x is equal to x, this is an identity because no matter what value we give to x, it will always be true. If x is 5, 5 equals 5, that's true, etc. This is an identity. Y squared is equal to y times y. Again, no matter what value y takes, this equation will be true. 1 times a is equal to a. This is also an identity. No matter what value we assign to a, the equation will be true. So these are all probably pretty obvious and intuitive. But what we're going to see with trig identities is the equations will have trig functions in them, and we'll see how we can use these types of identities. So let's go through a few of the identities that we've already seen. First are the Pythagorean identities. The most basic form of the Pythagorean identity is cosine squared of x plus sine squared of x is equal to 1. So again, no matter what value we assign to x, and we know that x is going to be an angle, so no matter what angle we give to x, the left side will be equal to the right side. And then there are two other versions of the Pythagorean identity. If we divide through each term by cosine squared, we get 1 plus tangent squared of x is equal to secant squared of x. And then if we divide the first version of the equation through by sine squared x, we get cotangent squared of x plus 1 is equal to cosecant squared of x. So those are the Pythagorean identities. Next we have the even and odd identities. The trig functions that are even are cosine. So cosine of negative angle is equal to cosine of that angle. Same for secant. The other four trig functions are odd. So here for the odd identities, we have tangent, sine, cotangent, and cosecant. Each of these functions are odd. So what that means is if we take the negative of the angle, that is equal to negative of the trig function of that angle. So there are two more sets of kind of the elementary trig identities that we've seen already. We have reciprocal identities and quotient identities. So here are the 6 reciprocal identities, and I think you've probably we've seen all of these already before, and let's just kind of give an example of why this works. So let's pick an angle. Let's say theta is, 60 degrees. So sine, what this is saying is sine of 60 degrees is equal to 1 over cosecant of 60 degrees. Well, sine at 60 degrees, that's on the unit circle, that's going to be root 3 over 2. That's equal to 1 over cosecant of 60 degrees. Well, cosecant of 60 degrees is just the reciprocal of sine of 60. So this is 2 over root 3. And if we multiply the top and bottom by root 3 to rationalize the denominator, we get root 3 over 2. So we can see that those are equal. So that same idea is going to work for all of these reciprocal identities. And in fact, any identity we have, if we pick an angle, substitute it in, the left side is going to equal the right side. And then lastly, we have the quotient identities. We can write tangent of theta as sine of theta over cosine of theta. And then cotangent of theta is just the reciprocal of that, cosine of theta over sine of theta. All right, so those 4 groups of trig identities, the Pythagorean identities, even and odd, reciprocal, and quotient, these are ones we've seen already that we'll be using here in this video. So the first thing we want to be able to do with these trig identities is to be able to take an expression that has a trig function or multiple trig functions in it and simplify it down. And what we mean by simplifying, we want to get down to a single term if possible. We want to get down to one trig function if possible. So if we have an expression that has sine and cosine in it, we want to get everything just in terms of sine, for example. And then lastly, we don't want any fractions. And all of these are if possible. We may not always be able to achieve each of these three items, but that's going to be the goal. So let's look at a straightforward example here. We want to simplify the expression sine of x, let's write a sine a little bit better, sine of x times cosine of x times cosecant of x. Alright, so when we look at this expression, we can see that it is one term, so we're good there. We don't have a trig function, so we fail on that, but we do not have any fractions. So is there any way we can write these three different trig functions, sine, cosine, and cosecant, in terms of just one trig function? Well, a helpful rule, or a helpful first step, is to write everything in terms of sine and cosine. Now this doesn't always work, and that's something that will be kind of a repeated theme when we're working on these types of problems, is there's not one thing that always works. We kind of just have to try different things until the light turns on for us. But in this case, we already have sine and cosine, but cosecant of x, that's the same as 1 over sine of x. So if I rewrite this whole expression, I have sine of x times cosine of x times 1 over sine of x. And what we'll see is that this sine of x and this sine of x can cancel out. So what we end up with is just cosine of x. And that's as simple as we can get. So we've gotten down to a single trig function. Alright, here's another example. This one is going to use the identities, the even and odd identities. So anytime we have a negative argument in here, that should trigger us to look at the even and odd identities. So sine is an odd function. So what that means is this is equal to negative sine of x. Cotangent is also an odd function, so this is equal to, let's write this like this. Cotangent of negative x is equal to negative of cotangent of x. Alright, so when we multiply a negative times a negative, that gives us a positive, so we could write this as sine of x times cotangent of x. And what I want to do here is we have a single term, but we have two different trig functions. So we have sine and cotangent. So again, I'm going to take cotangent of x and write it in terms of sine and cosine. So sine of x, cotangent is the reciprocal of tangent. Tangent is sine over cosine. Cotangent is cosine of x over sine of x. So when we multiply here, the sine of x is cancel, and we end up with cosine of x. That's just a coincidence that we got the same thing as we did on the previous example. Alright, so let's ramp it up a little bit. We need to simplify this expression. 3 sine cubed of theta plus cosine squared of theta plus 2 cosine of negative theta times cosine of theta. Now, what I'm going to do here, oops, I made a mistake in how I was writing this. This is not cosine squared. This should be cosecant. Hang on. I'm looking at my notes. Give me one sec. Okay, so the cosine squared of theta is actually correct, but in that first term I want to have 3 sine cubed theta times cosecant theta, and then everything else was correct. Okay, so this is what we want. So what I'm going to do is I'm going to rewrite cosecant of theta in terms of sine. So this is going to be 3 sine cubed theta. Cosecant of theta is 1 over sine of theta. And I'm just going to do that one step here at the beginning. All right, so what we have in this first term over here, I have 3 sine cubed theta, and that's getting multiplied by 1 over sine of theta. So this sine will reduce the sine cubed to sine squared. So we end up with 3 sine squared of theta plus cosine squared of theta plus, now this cosine of negative theta, again we want to think of the even and odd identities. Cosine of negative theta, well, cosine is an even identity, so what that means is cosine of negative theta is the same as cosine of theta. So this will be plus 2 cosine of theta times cosine of theta. And when we multiply this together, 2 cosine theta, that's kind of like 2x times x, right? We get 2x squared. So 2 cosine theta times cosine theta is going to be 2 cosine squared theta. All right, so let's bring everything else down. 3 sine squared theta plus cosine squared theta plus 2 cosine squared theta. So these two terms, these are like terms. Okay, if we think about this in algebraic, that's like, or an algebraic viewpoint, that's like saying x squared plus 2x squared, right? That would give us 3x squared. So cosine squared plus 2 cosine squared is going to be 3 cosine squared of theta. Bringing down that first term. Okay, so we've simplified this a little bit from 3 terms down to 2 terms. And one thing we're going to do here is oftentimes we'll want to look for a common factor to factor out. And in this case, we have a 3 in each term. So we're going to write 3 sine squared of theta plus cosine squared of theta. And what this expression is right here, that's a Pythagorean identity. This is very common. We're going to see this repeatedly. Sine squared theta plus cosine squared of theta. And that is equal to 1. So we end up with 3 times 1 is equal to 3. So that's what this expression simplifies down to. All right, this example is the first one where we have fractions. So we need to remember the general rules of fractions. In order to add fractions, we need common denominators. When we're multiplying fractions, we go straight across. When we're dividing fractions, we multiply by the reciprocal of the second fraction. So all of those basic rules of fractions, we need to remember how to use them. So in this example, I want to add these 2 fractions together. Now, in order to add these 2 fractions together, I need to get a common denominator. The first thing to notice, though, is, again, when we have a negative argument, we want to think of the even and odd identities. So cosine is even, so this is the cosine of negative x is equal to cosine of x. Okay, so we have 2 fractions, we want to add them together. In order to do this, we need to multiply each side by the least common denominator. So the least common denominator here is going to be 1 plus cosine of x times 1 minus cosine of x. All right, so in practice, let's think about just how we would add 2 fractions. 1/3 plus 1/2. Well, the least common denominator here would be 6. So we don't need to necessarily multiply both fractions, the top and bottom, by 6. What we want to do is we want to get the denominator to be 6. So in the first fraction, we're going to multiply the top and bottom by 2, because 2 times 3 in the denominator will give us 6. Then in the fraction on the right, we multiply the top and bottom by 3, and that'll give us a denominator of 6. So that's the idea with the equation, or I'm sorry, the fractions that have cosine in them. So what we're going to do on the left fraction, we're going to multiply the top and bottom by 1 over cosine of x. And then on the right fraction, we're going to multiply the top and bottom by 1 plus cosine of x. And doing so, we're going to end up with a common denominator. So in the numerator, 1 minus cosine of x, and then in the denominator, we get the common denominator we've already identified. And then on the right fraction, it's very similar. 1 minus cosine of x, 1 plus cosine of x. Okay? So now that we have a common denominator, we can write these two fractions with the same denominator. So in the numerator, I'm just going to write everything together, just for the sake of clarity. 1 minus cosine of x, 1 plus cosine of x. Okay, so we have a single fraction. In the numerator, I can do some cleaning up. I have a negative cosine of x and a positive cosine of x, so those will cancel. In the numerator, I have a 1 and a 1, so that's going to give us 2. In the denominator, I'm going to multiply these two binomials out. And these two binomials are a difference of, this comes out to be a difference of squares when we multiply. So if we FOIL, I do 1 times 1 is 1. 1 times positive cosine of x, positive cosine of x. Multiply these two, I get negative cosine of x. And then negative cosine x times positive cosine of x is negative cosine squared of x. Bring this up here. So we see in the denominator, cosine of x and negative cosine of x are going to cancel. So we end up with 2 over 1 minus cosine squared of x. Now, this is actually a version of the Pythagorean identity. If we recall, sine squared of x plus cosine squared of x is equal to 1. Well, if we subtract cosine squared of x from both sides, we end up with sine squared of x is equal to 1 minus cosine squared of x. So anytime we see sine, cosine, or any of the trig functions getting squared, we should think, ooh, is that a possible variation of the one of the Pythagorean identities? And in this case it is. So this is going to be equal to 2 over sine squared of x. Okay? And so if we recall, 1 over sine of x is equal to cosecant of x. So let's see here. 2 over sine squared of x. Well, that looks like I can do something to get a cosecant in here. So 2 times 1 over sine squared of x. Well, 1 over sine squared of x is the same thing as cosecant squared of x. So this can be simplified to 2 cosecant squared of x. And we've hit everything we want. We have a single term, a single trig function, just cosecant, and we don't have any fractions. Alright, this last simplification example is a little bit different than the previous ones. Here it's saying, take this expression, cosine of x divided by 1 plus sine of x plus tangent of x, and we want to write that in terms of cosine. So in other words, we want to change tangent, tangent of x and sine of x. I'm going to remove those and only have cosecant of x in this expression. So what we said previously, one strategy is to always change everything in terms of sine and cosine. So tangent of x is equivalent to sine of x over cosine of x. I'll bring everything else down. Okay, when we have fractions, we can think about getting a common denominator. So I'm going to multiply this fraction on the left, the top and bottom by cosine of x, and then the fraction on the right, I'm going to multiply the top and bottom by 1 plus sine of x. Okay, so when I multiply these two sets of denominators together, I know I'm going to get the exact same denominator. I'm going to end up with cosine of x times 1 plus sine of x. I'm not going to multiply it out yet. And then in the numerator, I'm going to get cosine of x times cosine of x. That's cosine squared of x. And then up here, when I distribute, I get sine of x plus sine squared of x. Now, as mentioned, anytime we see any of the trig functions getting squared, we can think about one of the Pythagorean identities. So this is cosine squared plus sine squared. That is going to be equal to 1. So in the numerator, we get 1 plus sine of x divided by cosine of x, 1 plus sine of x. Okay? And so what happens here is this expression and this expression are going to cancel. So we end up with 1 over cosine of x. And that's what we want. We've written everything in terms of cosine of x. Now, this doesn't really adhere to the 3 rules that we laid out at the beginning of the video when we said we didn't really want fractions. So while this is equivalent to secant of x, we want to write everything in terms of cosine. So 1 over cosine of x is what we want. So simplifying the trig expressions like this is useful, but ultimately where we're going is we want to be able to verify trig identities. So we'll see what that means by going through a few examples. Alright, this example says to verify that tangent of x times cosine of x is equal to sine of x. And what this means is we want to work with this equation that the left side is equal to the right side. Now we need to be able to show this exactly. So all of the simplification examples that we've just done, that is just leading into this, because what we'll do is we'll try and simplify the left-hand side and or the right-hand side in order to make these exactly equal. So as mentioned, we often will try and write everything in terms of sine and cosine. So tangent, we can write in as sine of x over cosine of x times cosine of x is equal to sine of x. And when I multiply these two together on the left-hand side, the cosine x's will cancel. We'll end up with sine of x is equal to sine of x. And there we go. They're exactly equal. Now, it may seem obvious or tempting to stop at this step, the second to last step. However, we haven't shown this as straightforward as possible. We want these to be precisely equal to each other. Alright, so that is a fairly straightforward example. We only had one thing to do. We used one identity. And now let's look at a couple of examples that get a little bit more complicated. Alright, this example says to verify that secant squared of beta minus 1 divided by secant squared of beta is equal to sine squared of beta. So verify that that is an identity. And I forgot on the previous to finish that sentence, verify that tangent of x cosine of x is equal to sine of x is an identity. That's what we're trying to prove. Okay, so a couple things we could do here. We could try and convert everything into sine and cosine, right? Secant squared of beta is equal to 1 over cosine squared of beta. So we could replace these secant squareds with 1 over cosine squared. That's definitely a possible route we could take. However, I'm going to use one of the Pythagorean identities. Remember, anytime we see a trig function squared, we should be thinking about the Pythagorean identities. And the Pythagorean identity that makes sense here is 1 plus tangent squared of beta is equal to secant squared of beta. If we subtract 1 from each side, tangent squared of beta is equal to secant squared of beta minus 1. So I can replace the numerator here with tangent squared of beta. And I haven't done anything to the denominator yet. Okay. Now what I'm going to do is convert everything in terms of sine and cosine. We could have done that first and then simplified the complex fraction. But by doing it this way, things will simplify a little bit easier. Okay, so what we have is sine squared of beta over cosine squared of beta. That's coming from the tangent squared in the numerator. And then 1 over cosine squared of beta is coming from secant squared of beta in the denominator. Now when we have a complex fraction, that is just a fractions within a greater fraction, if the denominators are the exact same, those can be canceled. So we end up with sine square root of beta is equal to sine square root of beta, and we've got it. Got the left side equal to the right side. So one thing I want to highlight here in this example is that notice how all of the equal signs are roughly lining up vertically. This is how I want to see these types of identity problems done. Sometimes students will, this isn't a good example for me to show what not to do, but sometimes students will put an equal sign, an extra equal sign on the same horizontal line. Every time you make a change, do it directly below. So just do one thing at a time, align everything vertically, and try and just keep everything on the left side isolated and everything on the right hand side isolated. Alright, so last example here. We want to verify that this is an identity. Tangent to the fourth of x plus tangent squared of x is equal to tangent squared of x times secant squared of x. I'm actually going to show two different ways that we could solve, or that we could verify this. So, first thing I'm going to do, the first way I'm going to do this, I'm going to turn everything into sine and cosine. So tangent to the fourth, I can rewrite that as sine to the fourth of x over cosine to the fourth of x plus sine squared of x over cosine squared of x is equal to tangent squared, which is sine squared of x over cosine squared of x times 1 over cosine squared of x. On the left-hand side, I'm going to get a common denominator. The common denominator is going to be cosine to the fourth. So what I need to do is, with this second fraction, I need to multiply the top and bottom by cosine squared of x. Okay, so what we end up with on the left-hand side is sine to the fourth of x over cosine to the fourth of x plus sine squared of x cosine squared of x divided by cosine to the fourth of x is equal to, now this is, I'm going to show you what not to do, what I was referring to on the previous example. What sometimes students will do is, when multiplying these two together, they'll write an equal sign here and write sine squared of x over cosine to the fourth of x. That is not how you should be doing this. We need to write that step directly below. Sine squared of x divided by cosine to the fourth of x. And the reason is because it's not always clear when students do this whether this expression is equal to the right-hand side or is this equal to the left-hand side. It's just easiest if we have a single equal sign in each horizontal line. Okay, so on the left-hand side here, I have a common denominator, so I can add these two fractions. So sine to the fourth of x plus sine squared of x cosine squared of x divided by cosine to the fourth of x. And what we notice is that the denominators are the same on both of these, but the numerators are not the same. So what we can see is that on the left-hand side in the numerator here, there's a common factor in each term. Okay? So this is kind of, if we're thinking about this algebraically, it's kind of like we have x to the fourth plus x squared y squared, where x is sine and y is cosine. What we see here is that there's a common factor of x squared. Okay, so if we factor out x squared, we would end up with something like this. So what we can do is we can factor out sine squared of x, and we're left with sine squared of x plus cosine squared of x divided by cosine to the fourth of x. And this right here is our best friend, the Pythagorean identity, and that's equal to 1. So what we end up with in the numerator is just sine squared of x divided by cosine squared of x, and that does it for us. Okay, so in this case, we may be able to simplify the left-hand side and the right-hand side a little further, but it doesn't matter. We've achieved our objective, which is to prove that the left side and the right side are exactly equal. All right, and the second way I'm going to do this exact same verification, this actually came from a student in a previous semester. There's a much easier way for us to go about verifying this. On the left-hand side, if we factor out tangent to the second of x, and then what we're left with is tangent squared x plus 1. Well, tangent squared of x plus 1, that's a Pythagorean identity, and that's just equal to secant squared of x. And so really we just have a single step there. So that is much quicker and cleaner, and the issue is being able to identify that we have a Pythagorean identity in there. And that's what I didn't at first see. So the whole reason I want to show that there's more than one way to do this problem is because that is true for any of these verification problems. There is oftentimes a short way, there's oftentimes many different longer ways to do these problems. And there's not really one correct way. There's many wrong ways, but there's many correct routes we could take to get to a final verification. And so when we're doing these problems, the answer to this problem is all of this work. Okay, so we don't ever put a box around the final step here. It's not something we would be doing. The answer is all of the steps that we're taking. And so because we could take different routes to get to the final line, we need to be able to show all of those lines. And then the final thing I want to say about these types of problems is, for many of us, if we've never done something like this, if we've never done these problems before, this is very challenging. And this is kind of a demarcation point in your math studies. Everything kind of leading up to this point has been characterized by algorithms and following steps and procedures to get correct answers. In other words, if you had the correct type of problem, you can just follow the steps. So for example, if you have a quadratic equation, something like this, and you want to solve that, you think, all right, how do I solve a quadratic equation? I can use the quadratic formula. I just plug everything into the quadratic formula and I can get the answer. That is not how these types of verification problems work. I cannot tell you if you do this first every time it's going to work. You really need to think more analytically. And so this type of thinking is going to be what you will need as you progress from here on out in your math studies. This is a vital part of calculus. To being successful in calculus is being able to analyze a problem and figuring out what different skill or tool do you need in order to answer it.